Hello and welcome to today's daily Leetcode challenge. Today we'll be solving question 1335, minimum difficulty for a job schedule. This is a hard level problem, and let's jump right into the description. All right, so 1335. So you want to schedule a list of jobs in D days. Jobs are dependent, meaning to work on ith job, you have to finish all the previous j jobs, where j are just everything preceding I, including 0. Okay, so we need to complete all the jobs before I. You have to finish at least one task each day. Okay, so they're called tasks, but one job each day. The difficulty of a job schedule is the sum of the difficulties of each of the D days. The difficulty of a day is the maximum difficulty of a job done that day. All right, so one more time, we have some number of days called D, and we have some jobs. The jobs have to be completed in order. Within one day, you can complete a job. The difficulty of that job is going to be given us in the difficulty array. The difficulty of that day is the maximum difficulty of a job done that day. You're given the integer array difficulty jobs and an integer d. The difficulty of the ith job is difficulty at index I. Return the minimum difficulty of a job schedule. If you cannot find a schedule for jobs, return -1. All right, so in my own words, what does this kind of map to in the real world? We're given some number of tasks. Each task has some difficulty. It can be arbitrary. These tasks have to be completed in order, and you're given some number of days to complete them. Within the day, you can complete some number of days, but each day has to be filled up, meaning you have to complete at least one task that day. The difficulty of that day is going to be characterized by the maximum difficulty of a job done that day. So if we have 10 jobs done in one day, going from 0 to 9, the difficulty of that day is going to be 9. All right. So how do we go about this? Let's look at some examples. So we have the job difficulty array indicating which jobs have to be completed. We have the 6, 5, 4, 3, 2, 1, a descending array. Let me get rid of that. And 2 days. Well, by judging by this picture, the easiest way to go about this is to complete as many jobs as you can right away. So 6 through 2. And then last day is going to be, since the last day is going to be characterized by simply one job, it's beneficial for us to choose that one and just do one. So 6 plus 1, 7, boom. We have 7 as the total difficulty of the schedule. This is extremely intuitive, because if we were to choose anything but the first 5 tasks, we would have had to complete the other 2 the next day, increasing our difficulty of the overall schedule. Now, what if this was the other way around? What if this was ordered in ascending order? Well, then, if this was ordered in the ascending order, meaning that we have 1, 2, 3, 4, 5, 6, well, then it would be beneficial for us to only do one job on the first day and do the rest 5 on the next. All right, so there's some variation. We know that it's not good enough just to it's not good enough just to pick out what the minimum difficulty for a day is. We have to have some knowledge of the future schedule for days. Because what I was thinking initially is, well, why not just complete all the difficult jobs initially, right? Just judging by this example, why not just complete all the difficult jobs, as many difficult jobs as you can first, meaning that these five, um, and then just complete the easiest ones last. Well, that doesn't work if the array of tasks is in ascending order. All of a sudden there you would need to adjust the strategy. You would need to complete all the easy tasks first and then the difficult ones. So a primitive and a naive approach where you just pick a strategy of completing some difficult or easy tasks initially and then continuing with the harder or easier ones doesn't work. Example 2 shows an example of a invalid output, and let me remember, what does -1 mean? If you cannot find a schedule for the jobs, so this is an invalid schedule, and why is that? Because we have 4 days and we have 3 tasks. So you could, I see. This is not possible because you are completing, oops, did I just, you're completing the 3 tasks in what, 3 days, and then you have 1 day that's going to be just left jobless or taskless. That doesn't work. And then this one, difficulty is 3. Difficulty of the schedule is 3 because each day you can complete a task that is the difficulty of 1. Over the course of 3 days you have 3 tasks, and the sum of them is 3. Okay. The difficulty array is pretty significant, and the difficulty of tasks is also going from 0 to 1,000. All right, so how do we approach this? Well, because of the statement that you need to have knowledge of the future, you need to have knowledge of what is going to be the optimal schedule for days, not including the current one. Just because of that statement, it seems to me like this is going to be another dynamic programming approach. Let's figure out some examples maybe that we can work off that aren't as simple as the ones given here, to give us some give us something to work with. I'm going to make up a difficulty array, and let's work through this. Let's say that this is the difficulty array, and then the number of days are, let's say 6. Cool. Okay. What would be the strategy here? We could okay, wait, 6 days. So first of all, to stay in line with the requirement that at least 1 job has to be completed each day, we have to limit ourselves to what we could even complete in 1 day. Let me outline that with, let's see, 1, 2, 3, 4, 5. We are only able to complete or to even consider these 3 jobs for the first day. Why is that? Well, because if this is completed in the first day, then 2nd, 3rd, 4th, 5th, 6th, we have all of our days mapped out. For the first consideration, we need to figure out if we're just going to complete this one, these 2, or these 3. each time we consider one of these options, we have to take into account that the rest of the schedule is completely unknown. But what if we can infer or assume that the rest of the schedule is going to be constructed optimally with an optimal solution? Well, then in that case, all that's left for us is to first of all pick between these three options, and finally then construct out of these three options, we'll pick the optimal, but also figure out what the algorithm is going to be to construct the optimal solution for the further path. And it seems like if I'm able to pick the optimal out of these three, the later portion is going to be similar. The later days are going to be similar with this approach, just cutting off whatever we've considered for the first day, right? If we pick out later for the optimal solution, if we pick out later what the what the optimal solution is going to be later, then we actually have this problem solved recursively. Okay, so then what could be the consideration, the logic here? Well, let's have a function, a recursive function that we're going to be calling over and over again. With the difficulty array, we need to know what number of days are left, I guess, days left, and then what the current place is that we're considering, right? So initially we're going to be looking at just here, and 5 days left. But once we figure that out, we're going to, in our code right here, we're going to be considering what is the optimal solution for well, the same. So basically let me index idx. Out of, in this code, we're going to be considering what is the same df, but days minus 1 and index plus 1. What is df days minus 1 index plus 2 in the case where we choose this? And then finally function df day minus 1 index plus 3. We're considering which one of these is going to be the optimal. We're going to pick that optimal. The optimal is going to be telling us what is the best solution out of the, when we pick index plus 1, plus 2, or plus 3. That is the rough outline. Let's get into the code. I'm thinking that probably be good to start off with defining some edge cases. Or not some edge cases, defining the function itself, roughly what it's going to look like. It's going to be a recursive function. I said that the job difficulty is going to be the array that we pass just from function to function, although this doesn't actually have to be passed. We can say days left and the index are the only two things that we're passing to our function, because that identifies the sub-problem. Let's see, if days left is equal to 1, meaning that we are now looking at maybe our last consideration here. If the days left are 1, well, we have a subarray starting from index, going all the way to the end, and we have to pick out the we have to pick out the max task difficulty out of that, right? So max, so that's just going to be return max of the job difficulty, starting with IDX and going to the end. That's if we have 1 day left. Then we need to find what is going to be the max difficulty across all the considerations that we have to make right now. Max difficulty is going to be initially just the job difficulty IDX. Days left is going to be decremented by 1. But really what we're doing here is what we're doing here is going over all of these considerations. So from range starting at index to and here it's going to be, let's use the length L equals job difficulty. Let's say L minus what was this? L minus the days left. L minus days left. And since this is exclusive, we also have to do +1. So L minus days left tells us how many options we have to consider during this current consideration. And actually, this is also going to be +1 because we've already constructed the max difficulty, or we've already considered the current max difficulty. Okay, then let's what is the max difficulty of all of these 3 in order? Well, it's going to be the first one, then the second one, then the third one. This is already considered first, so we say max, and then the job difficulty of the I. That seems about right. So the other is now going to be the recursive of the rest of the solution, the optimal solution of the rest of the array. That's going to look like recursive days left, we already reduced by 1, and index is going to just be I believe. Cool. Right? Then res, the result, the optimal solution is just going to be the minimum, because we do want to find the minimum job schedule of the what is this now? The res itself, and then the max difficulty plus other. Return res. So I think that we have outlined the recursive definition for what it means to consider 3 options plus an optimized schedule for the days that we didn't consider yet, and the edge case, the final case. It's not an edge case, it's the base case where days is equal to 1, and you simply pick out the maximum task from the array that we have left. Okay, so now that we have this, let's think of what else needs to happen. There are some edge cases here. In the case of the example 2, when we have if d is greater than L, return -1, and else I believe that it's enough for us to do this. We have days left starting with D, and the index of 0. And I believe that that's pretty much it. Let's see if this works. Now, what did I mess up here? Days left. Invalid syntax. What did I do? Oh, in range. Awesome. Wow. All right, let's see if this works. There might be some complication here. We are doing something that probably shouldn't be doing. We are rerunning some. Oh, and this is example that I. This is the example that I used. Okay, wait 1 second. I think I might be use test case. Let's see if this. Okay. Sorry, so I had the job that I was considering is +1. Okay, sorry. Okay, let's see if this works now. Difficulty I minus. Okay, we have a time limit exceeded. Okay, and this is what I wanted to get to. We have a time limit exceeded. Why? Well, because we are actually, what we're doing is we're sometimes calculating the same thing over and over again. When we call rec days on a solution, on a question of what if we only consider 1 for the first day, and then we, no, sorry. How do I phrase this better? The better way to say this is, let's say that, and I'm going to be doing this in yellow, other at some point gets called with this subarray. In which cases does other gets called here? Well, this is one case where we consider 3 for the first, and then other gets called on index starting from 2. But this same thing is going to be called again when we consider 2 and then 1 for the next day. And then when we consider 1 day, with the next day being as 2 or 1. So we're actually doing the same calculations for other starting at 3 multiple times. Well, what if we could only calculate it once and then use the solution for later approaches? And that's, I think, is where the dynamic programming is going to, that's where the dynamic programming array or another form of memoization is going to come in. Let's say dp is equal to 0 times L for in range over all the days starting from 0 and going to 1. I want the rec of the same D0. And let's actually just define this here. Let's not even modify the array. And I want to be returning dp of d and 0. Okay. Okay, so what modifications here? Well, let's, the most important one is if we've already calculated this, and by the way, the first dimension represents the days that I have left. Those are going to be the starting point, and then the on the x-axis, or the second dimension, is going to be representing the no, wait, sorry. The first dimension is going to be representing where in the array I'm starting from. The second is going to be the days that I have left. So I could be calculating this starting from here with either 3 days left, or 4 days left, or 5 days left right here. Because I could have considered taking in my first day just the first task, 2 tasks, or 3. In all 3 cases, the this optimal solution is going to be different. It's going to be the index is still going to be 3, but the number of days I have left are either 3, 4, or 5. Okay. 3 or 4 or 5. And yes, we have this DB. We have the days I've left, starting from 0, and let's see what goes here now. If days left for the, this is for the index, does not equal 0, then simply return, right? If we have 1 day left, instead of returning now, we're going to be memoizing it. This is going to be days left with an index is equal to this, and then simply return. This doesn't change. This doesn't change at all, but what does change is what we do here. Instead of returning and calculating res this way, we're actually going to be memoizing it here. dp days left plus 1 idx is equal to res. We don't need this here anymore. Res is still going to be the minimum of these, but okay, so what does other do? Other here is now going to be, let's see, other, I want this to initially be to the left of I, and if other is equal to 0, meaning that we haven't yet calculated it, let's calculate with days left, which is already reduced. We have the index here, and the other is now equal to, now that we've calculated this, dp days left I, which is almost the same as what was here before. And finally, we have res, which is the minimum of what we just found, plus other, the minimum difficulty. And yeah, I believe that's it. Let's run, see if this works. Difficulty plus, okay. Awesome. Submit. So yeah, by the way, what we're doing there, 0. Let's see, wait, if sum of job difficulty is 0, return 0. What we did here is memoized, or it's not that bad. we memoized some of the solutions so we don't have to solve them for next time, but the logic with what was done previously recursively is pretty much identical, except we're using this intermediate data structure to memorize some of the solutions. All right, this was a pretty tough one. I would say that it's if you get it, that's good enough. I'm not gonna compare it to other solutions. They might be even more difficult to explain or to understand. Yeah. Oh, okay, with that, let's end today's video. Thanks for watching. Please like and subscribe, and I will see you later. Bye.